Welcome to our video about hyperbolas. Now, before I step aside to reveal the board, I do want to say there's a lot of different pictures on it. I did not want to have to spend time in the video drawing them. So I will explain each of them as we get to it. And yeah, so just don't be intimidated by all these extra things like, whoa, he put so much on the board. We'll get to it in time. So hyperbolas are an interesting type of conic section. They come about kind of, if we like run with the metaphor of if we squish a circle, we get an ellipse. Well, if we keep squishing that circle, eventually it's just going to pop like a balloon. And when it pops and it kind of explodes outwards, that's what happens. That's what gives us a hyperbola. Now, you might hear that hyperbola sounds very similar to parabola, and they are related. Conic sections, after all, are all intimately related to each other. So a hyperbola, looking at this first graph, is made up of two different branches. Each part of that, each half of the hyperbola is called a branch. Now, we might be tempted to say a hyperbola is just two parabolas looking at each other, but that is not true. A parabola continues to curve. As long as it goes on, it will continue to curve. But hyperbolas, on the other hand, if we zoom out really far, they get really flat along the edges. And so that's a very subtle distinction that we can't always see on a small scale when you're just graphing part of the shape. But hyperbolas will eventually flatten out, whereas parabolas will not. So the definition of a hyperbola will sound very similar to the definition of an ellipse. So this time we have two fixed points. Each of them is called a focus. Together they are the foci, and we have our two branches of the hyperbola. So the hyperbola is the set of all points, the difference of whose distances to two fixed points is constant. So if we take any point along either branch and we draw a line to the first focus and a line to the second focus, and we subtract that smaller distance from the larger distance, it will always give us a constant value for any point along the ellipse, hyperbola, for any point along the hyperbola. The difference between the ellipse and the hyperbola is the difference. An ellipse, we have the sum of the differences. A hyperbola, we have the difference of the different distances. A little tongue-tied there. So that's really what this picture represents, like the geometric, where does this come from? Now we're going to look down a level to start naming some vocabulary. First thing to notice, some of these hyperbolas open to the left and right. Those we call horizontal. Some of them open up and down. Those we call vertical. This dotted line has a special name. It is called the transverse axis. Transverse essentially means it goes across. So it's the axis that goes across the two branches. And I want to label these points. So obviously at the center, we have the center. If we go out, each of these is called a vertex. It looks like the vertex of a parabola, except this time there are two of them, one for each branch. And then inside, not between the branches, but inside each branch is another focus. So there's a lot of focus going on. The problem with abbreviating center as the letter C is that the letter C does refer to a distance. So if we think of, I'm going to erase this this word right there. So the distance from our center to the focus, just as with an ellipse, is the focal length. So this is our focal length, and we call it C, which is why I had to erase the C's for center. The distance from the center to the vertex we call A. Now, when we were defining an ellipse, we started with A and B, and then we found C, the focal length. Hyperbolas are a little bit messier. We start with A and C, and then we have to figure out B from there. There are a lot of geometry and pictures that I can't always follow easily without reading through a list of steps. We find that B is this point in the middle of nowhere, or the distance to the point. So now I want to shift our focus from the middle picture down to the bottom pictures. And there's a lot of information in these pictures, so I'm going to say some of that, and then we'll get back to how this ties into the letter B. So I mentioned earlier that hyperbolas flatten out. So these dotted lines, dashed lines that form an X through the center, those are the asymptotes of the hyperbola. As we get further and further from the center, the hyperbola gets closer and closer to the asymptote. And so these asymptotes are both straight lines, and they have opposite slopes. So we have a positive slope and a negative slope, but if we draw out this triangle right here, and we think of it as rise over run, this positive slope going up is the same as the negative slope going down, just opposite directions. So they have the same but opposite slopes, our two asymptotes. We said earlier that the distance from the center to the vertex is A. So the distance from the center to this point in the middle of nowhere is B. Likewise, if we have a vertical hyperbola, the distance from the center to that point in the middle of nowhere is B. And this distance comes from the asymptotes. Because if we draw a box that is 2A across and 2B high, or vice versa, if it's a vertical hyperbola, the asymptotes will go through the corners of that box through the center. So if we draw out the rest of this line, so we have a B to the center, a B to the bottom, that is what we call the conjugate axis. That is not vocabulary we use often. So I will frequently say the transverse axis because that's really important. But this conjugate axis tells us where we get the B from. Unfortunately, there isn't an actual name for this point. It's not a vertex. It's not even a covertex. In my head, it makes sense to call it a node so that there's some way to refer to it. It doesn't technically match the definition of nodes elsewhere in math, but it's the word that I prefer to use to name these points that in no other textbooks actually have any names. So we use our nodes and vertices to construct the box that allows us to draw the asymptotes that lets us more easily draw the branches of hyperbola. That was a very long-winded sentence for how we go from an equation to the graph, and we haven't even looked at the equations yet. So I'm going to step aside, allow you time to pause the video if you need to in order to write down these vocabularies. And then in about 2 seconds, I'm going to erase this all and we're going to talk about the equations. The equations for the hyperbola are almost identical to the equation for an ellipse, except for one key difference. Instead of having a plus sign, we're going to have a negative sign. So we'll have x minus h squared over a squared minus y minus k squared over b squared equals 1. So far, so good. In this case, however, it doesn't matter which is bigger, A or B. That's unimportant. A always comes with the first term, and B is always with the second term. A is the positive, B is the negative. So in this case, since our positive term is the x term, our transverse axis is going to be horizontal. So if I sketch out, our center, our vertex, our focus, then this axis goes left and right, and our branches open to the left and the right. So if we're going to rotate this picture so that instead the transverse axis goes up and down, how would we have to change this equation? Take 5 seconds, pause the video, and try to predict how we can change the equation to switch the orientation of the hyperbola. So if you thought perhaps we need to switch A and B, like we did for an ellipse, that's not powerful enough. What we need to do is switch our x's and y's. Because our first term is still going to be a squared. And note that it's still y minus k and x minus h. But this time the y term is positive, and the y term being positive tells us the transverse axis is going to be vertical. So we'll have focus, vertex, center, vertex, focus. That was a bad line. So our branches end up opening up and down in the y direction. So I'm going to erase some of this real quick because there's still one more relationship. That's how we find our focal length. So if you recall from the last video about ellipses, I said that ellipses and hyperbolas have different formulas for the focal length. For a hyperbola, c squared is equal to a squared plus b squared. Now technically, while this looks identical to the Pythagorean theorem, it is not the Pythagorean theorem because it is not a statement about the sides of a triangle. It just so happens that the relationship is the same as the Pythagorean theorem, even though we are not describing triangles. In this case, C needs to be bigger than A. So I'm going to sketch out a small hyperbola. Remember, A is the distance from the center to the vertex. But C is the distance from the center past the vertex to the focus. So in this case, because C needs to be bigger than A, we have to add something to A squared in order to find C squared. And if that special extra amount is B squared. So take another moment, write this down, and then we'll come back with an example of graphing a hyperbola. So let's do y minus 2 squared over, let's do 9 minus x plus 1 squared. We'll do this one 16 equals 1. Now, some of these numbers might sound a little bit familiar. To make it work out a little bit more nicely, I am using a Pythagorean triple, but we'll see how it all works out. So our equation is y minus 2 squared over 9 minus x plus 1 squared over 16 equals 1. This is the hyperbola we're going to graph. We might be tempted to say that 16 is a squared because it's bigger, but because this is a hyperbola, even if it's smaller, a squared always goes with the first term, with the positive term. So what does that mean a is? Well, the square root of 9 is 3, and the square root of 16 is 4. So a is 3, b is 4. So this is helping us find those values that we're going to use to construct our hyperbola. Before we get there, we still need to find our center. So our center is going to be look at the first term. We have 2, and then from the second term, -1. And hopefully, as I was going through that, you're like, something's wrong. This is incorrect, because it is. When we're looking with an ellipse, we always put the x term first. So it's really easy to read the x coordinate and then the y coordinate. But when we're looking at a hyperbola, the x's don't always come first. And so we have to be careful to still grab the x value of the center from our x term. So if I look at x plus 1, this says that h would have to be -1. And if I look at y minus 2, that means k would have to be +2. So our center is -1, +2. So just keep in mind, since we don't always have the x term first, we have to be really careful to not switch our x and y coordinate of the center. It is incredibly easy. It is a mistake I have seen far more often than I'd like to admit. It's a mistake that I've made as well. So we just have to make sure we're paying attention to those little details. And then, let's see. I think now is a good time to draw my graph. So, I'm gonna make sure I've got enough space. Okay. So I'm going to start by plotting the center. So I'm going to go -1 and +2. This is the center of our hyperbola. Now, the first thing to do is to graph the vertices. So the vertices are going to be in the same direction as the direction of our first term. Y direction is vertical, it's up and down. So I'm just going to draw this little arrow here that visually reminds myself that I'm going to go 3 up and 3 down. And then I can draw a left and right arrow next to the B to remind myself that I'm going to be going left and right 4 units. So I'm going to start by going up 3. So that's 1, 2, 3. And then I like to put a V in the vertex so I know where it's going to be. Then I go down 1, 2, 3. This is my other vertex. And then I move left and right 4. So 1, 2, 3, 4. This is my first node. To the left, 1, 2, 3, 4. This is my second node. I try to make the nodes smaller than the vertices. Another very common mistake is drawing the branches on the nodes rather than the vertices, and then it's just flipped the wrong way. So keep that in mind. What we're going to do next, and this is where I really wish the other color markers would show up on the video, because the graph can look pretty busy. What we're going to do is construct a box that left and right sides are over here, going through the nodes. The bottom and top go through the vertices. So as lightly as I can, just going to use a dotted line to make this box. Is this box, and it's a little bit lopsided, but I'm writing on an angle. When we're doing things by hand, we are not going to be perfect, and that is okay. So this box is going to help me draw the asymptotes. So our first asymptote goes through one corner, through the center, and out the other corner. The other asymptote goes from the other pair of corners through the center. So we end up with these two dashed lines that form a big cross in the middle of our square. Now, I want to write the equation of the asymptotes, and I'm realizing now that I forgot to include that formula earlier. But because these are both linear equations, but we don't always have an exact y-intercept, we can't write the equations directly in slope-intercept form. Instead, we're going to use something called point-slope form, which is y minus k equals the slope times x minus h. So y minus k and x minus h, they come straight from the original equation. To calculate the slope, we need to remember rise over run. So we know that I went up 3 and over 4. So the slope is going to be 3/4. And then we need to fill in our other numbers. So we have y minus 2 equals 3/4 x plus 1. And this is technically only one of the two equations. And that's for the one with positive slope. To make it the equation for the one with negative slope, we just add a negative sign. So what I personally don't mind seeing is if you just want to write plus or minus 3/4 as the slope. And that's a more shorthand way of saying these are the two equations. They're just being written compactly at the same time. If you wanted or needed to write this in slope-intercept form, you would need to pick plus or minus and then do it twice. Distribute, combine like terms, solve for y. Pretty foundational math skills that I am completely confident you could do without me guiding you through it. So that's the equations of the asymptotes. Let me kind of put a box around this. But now I'm like totally running out of space. So I'm going to actually erase the equations of the asymptotes. If you need to write them down, still take a moment, pause, and then write them down. But we kind of still need that space. So we still need to plot and find the foci. So if you recall, focal length c squared is equal to a squared plus b squared. So a squared is 9 plus b squared is 16 which means c squared is 25. So c is 5. So if we start from our center and move 5 points to the right, that would be changing our x value. But anyways, to just plot that, this would be our focus. And then count 5 to the left, this would be our second focus. And then once I have them plotted, I can easily see from the coordinate plane like what the coordinates of those points are. Occasionally our focal length, maybe not occasionally, more often than not, our focal length will be an irrational number, like the square root of 52 or the square root of 34 or something strange like that. And in that case, we would just have the coordinate as it appears in the center plus or minus that value of the focal length, comma, whatever it is. Or perhaps, it's the first number, comma, then the y coordinate plus or minus the focal length. I did multiple examples with that in the written notes. If you're unsure about how to apply it, just go look at those. But once again, I kind of need this space, so I have to erase some of this. I'm also going to erase the center because I want to give myself just a little bit more room. So we are not yet finished. Just noticed another mistake. So our foci should have gone up and down because our transverse axis goes up and down. This is a good reason why not only is it important to label your points, but to pay attention to those labels. So our focus would be 1, 2, 3, 4, 5 points. So that's our focus up here. And then 1, 2, 3, 4, 5 down here. That's our second focus. Y term is first. Our transverse axis, which goes from focus, vertex, center, vertex, focus, is vertical. So yes, I apologize for that mistake. A lot of the steps for graphing conic sections are very straightforward, but because there's a lot of steps, you really have to make sure you're paying attention to those little details, or it's easy to get off track. So the very last thing we need to do is use the box and the asymptotes to draw in our branches. So I start at the vertex, and then I curl around to the left, and I curl around to the right. I'm not passing the edge of the box. I'm not passing the asymptotes. I'm using them as a guide to draw the branch. So again, on the bottom, I'm going to start and curl along the asymptote, and then in the other direction, curl along the asymptote. And that really wraps up graphing our hyperbola. Is it a lot of work? Yes, there's a lot of little details to keep track of. But I promise you, if you practice a few of them and get a hang of the process, it'll be really straightforward to graph them whenever you need to. If you want to see an example of graphing a hyperbola that has a horizontal transverse axis, look at the written notes. Otherwise, for now, this concludes our videos about conic sections. Hopefully, I'll be able to make some videos for Precalculus as well, but I'm not sure if we'll be able to get to that material this year, which would be upsetting. But considering the overall circumstances we're in, sometimes it just happens like that. So practice your hyperbolas, and that's it for now.